complete Unit 1. Okay? Unit 2, power of an algorithm. Yeah. Although I mentioned that Google AlphaGo AI story, yeah. So when you go back, you can search the web, yeah, to read a little bit about that story. Yeah. All right. But here, I want to use a relatively easy example to show you the power of an algorithm. Yeah? Yeah. We have a lot of examples like that. Our first example, problem 1, evaluate a polynomial. Okay. Evaluate a polynomial. I hope you know a polynomial. Okay. What is a polynomial? And you need to evaluate it. Okay. So let's look at the problem. Okay. Given a polynomial, so we have the representation like this. Yeah. That is a typical polynomial representation. Right? Yeah. You have coefficients. Right? All these A0, A1, they are given, known coefficients. Okay. X, that is the variable. So because that is the variable, unknown. Okay. When you do the evaluation, X will be given as the input. So you get an input for X. Now you need to plug into the function. You do the operations, right? Addition, multiplications, raised to the power, you do that. You find the value. That's the first problem. Okay. Yeah. Very simple, right? Yeah. Everyone can do it easily. Do you need an algorithm to do it? You may feel, I don't need an algorithm to do it, right? I just do it. Because it's trivial to do multiplications and additions. Okay. So I don't need any algorithm. Okay. All right. Now let's look at the details. Here, the coefficients given, that means when you write a program, you can assume the coefficients are available. Okay? Now, although we can pass coefficients as parameters, yeah, in real-world applications, yeah, but you can assume they are given. Okay, all right. Then, when you run this program or when you run this function, every time the x value is different. Okay. Coefficients always the same. Okay. So that's the problem. Okay. The question, how to evaluate the value of the function p of x efficiently. Okay. To get a correct answer, everybody can do it. Everybody in this class can do it easily to get the correct answer. But that's not our goal. Our goal is the efficiency. How fast can you get the answer? Okay? Yeah, our focus, efficiency. Yeah. So here you can see for this class, usually you do not even you get a correct answer, you're not very satisfied. You want to get the fastest way to find the right answer. That's more important. Saving time, the same as saving money, right? Yeah. So that's why 90% of the time we spend on that efficiency. Okay? All right. So here, this example, I give you the reference, section 6.5 and this page of our textbook. Yeah. So here you can see, because when I want to cover a topic, sometimes when I see one example is really good for this topic, so I will take from that place. Okay? So even I, jump. Yeah. So in this way, because in this way I can cover more material. So I can rearrange the order a little bit so I can cover more material. So this example, so if you want to look at the whole description, you can go to that page. Okay. All right. How do you get an idea about its efficiency? We look at additions, the number of additions, and then the number of multiplications. Okay. All right. So that's the question. So you may feel we don't need an algorithm, right? So because based on the formula, everybody, so if I ask you to write a program, everybody uses the same way to write a program. Is that true? Everybody uses the same way. Yeah. Maybe not. Yeah. So maybe not. Yeah. So anyone has idea? So you do not use the, calculator way. Let's assume calculator. Yeah. Because you know the order of evaluation, right? So when you see multiplication, you should do multiplication first. Okay? So then addition, Yeah. Anyone who may do this differently? Differently. So if you do that way, so you get the same result. So you get the same response time. Okay. So think about. We may have different ways to find the same result, but in different ways. Okay? All right. All right. So first, let's just use the straightforward algorithm. So the way, so everybody, 90% of the time, people will use. Okay? All right. So what do we do? Because we want to look at efficiency. How do we look at efficiency? We want to find the number of multiplications we need to calculate the polynomial. We need a lot of multiplications. Okay? How do we get a total number of multiplications? We need to look at each term. For each term, how many multiplications do we need? Yeah, each term. Yeah, general term. Yeah. So here, cut off a little bit. Yeah. So, yeah. I should next time when I create, I should move, slightly to the left. Yeah. Yeah. Because we have some room here, but not that part. Right. Right part. Yeah. So we need to count the number of multiplications to get an idea about the efficiency of your algorithm. Okay? So the question, can you do that counting? Counting number of multiplications? Although we have additions is easy, right? So you can count additions easily. Can you tell me how many additions you need to do? Yeah, that's important. Plus one or not? Tell me, plus one or not? Okay. N plus one. Yeah, I heard two answers. One student told me N. Another student told me N plus one. So here, you can see, here, this is a simple question for counting question. Simple counting question. Discrete math, you learn counting, right? Yeah. So here, we use your discrete math counting technique. Do you know a little bit? Or do you still have idea about that counting technique? Okay, many techniques. Okay. Here we use some simple technique. Okay, counting technique. In order to determine, so here, let me take, the first time. Yeah, so if you forget that technique, so let me remind you, or let me describe it the first time, because we will use this technique many times. Okay, so the first time, let me describe it. When you do this counting, yeah, because you feel it's pretty hard to give the answer about n or n plus 1. One must be correct. We just need to know which one correct. Okay? So counting. Let me tell you this simple technique. Okay. All right. This technique tells you when you do that counting, try to find the reference. Reference-based counting. If you find a reference, then you can do the counting in an easy way. So this technique called reference-based counting. Okay. If you find good reference, then you can do the counting easily. All right. Let me tell you the easy reference. This plus, we take the subscript as the reference. The first plus corresponds to the first subscript. Second plus, the second subscript. The subscript is our reference. Okay? When you reach the last plus, you get the last subscript. Now you tell me what's the answer. N, not n plus 1, right? Yeah. So if you find the right references, you can do the counting easily. Okay? So later we have many questions like that. Okay? A basic technique. Okay? Okay? Yeah. All right. So let's go to the next step. Okay. All right. Okay. So our next question, measure efficiency. We need to measure efficiency. Okay. Yeah. All right. Can we use execution time? Yeah, because we can clock it, right? But that's not reliable. Okay? When you clock it, first you do not know what computer is used. Is it relatively low-end laptop or a supercomputer, right? You don't know. Another thing is you do not know if the program is a good one or bad one. Okay? Yeah. Yeah, because even someone use a powerful computer but write a really bad program, still not very fast. Right? So there are many factors. We want to eliminate those factors. We don't want to consider computer factor, program implementation factors, Yeah. We just want to look at, without those factors, we can still see the efficiency. Okay. All right. So we use the number of additions and multiplications. Yeah. Two operations, additions and multiplications. Yeah. But if you compare these two operations, you can see multiplications more important than additions here because much slower, right? Multiplications much slower than addition. Do you have that idea? So here you may need to use the knowledge from computer architecture. Okay, 2700. Okay, so I don't know if you talk about that in that class or not. I taught that before. Okay, yeah. All right, so we should focus on multiplications, much slower. Okay? Yeah. In what category? So if I want to give you some number, the category is 1 to 10 ratio. Okay? So if the time you use for one multiplication, you can do 10 additions, 1 to 10 ratio. That big difference. So definitely you want to focus on the bottleneck. Multiplication, that's the bottleneck. Okay. All right. All right. Adding assumptions for analysis. Yeah, when we do analysis, sometimes we need to add reasonable assumptions. Otherwise, too much uncertainty. Okay. So we want to increase the certainty. So we want to add some more assumptions. Okay? Yeah. But it should be reasonable. Yeah. So given a polynomial like this, okay, each addition, let's assume, can we assume? Yeah, based on the, the background we have, we can make a reasonable assumptions. The first assumption, let's assume each addition takes 1 unit of time. 1 unit, certain unit. Okay? Yeah. We do not need to know what unit. Okay. Yeah. It should be in the category of certain number of nanoseconds. Yeah. So in the real world, that unit should be in a small number of nanoseconds. So I hope you know the nanoseconds. Okay? Yeah. How big it is. Okay. Yeah. So here I put that number, 10 to the 9th power of s, or 1/billionth of 1 second. How big it is? 1/billionth of 1 second. 1 second already pretty small, right? But you divide it into 1 billion. You take 1 of the 1 billion. That's the nanosecond. Okay? Yeah. So you know how fast it is. Okay. All right. Each multiplication takes 10 units of time. Yeah, 10 to 1 ratio. Yeah. That's the reasonable assumption, right? It may not be very precise, but pretty close. 10 to 1 ratio. Okay. All right. The question. Yeah. The reason we make this kind of assumptions, we want to simplify the setting. But still, the problem is the same problem as before, right? We do not change the difficulty. Okay? The same problem, but we just want to, make things looks more certain, so we can do the analysis precisely. Yeah. Okay. Yeah. All right. Now the question: what is the performance of the straightforward algorithm? You know what is the straightforward algorithm, right? Yeah. So now we need to do the calculation. Count the number of units of time we need if we run this, straightforward algorithm. Yeah. Then that's our starting point, because our next solution, we want to improve from this starting point. We want to do much better than this. Okay. All right. Yeah. So we really want to improve the efficiency significantly. Okay? We compare the number to see how much we can improve. Okay? Yeah. All right. Estimate the cost by counting. Cost. Okay? So here I use this word, the cost. Yeah. So here, our understanding of this cost, we know usually when we talk about the cost, we mean the money we spend, right? Yeah. But here we can extend it a little bit. It could be the time we use. That's also the cost, the time you spend. Because time can be transferred to money, right? So in the business, time can be transferred to money. So when we talk about cost, we can refer to time used. Okay? Yeah, that's reasonable. Yeah. Yeah. All right. Number of additions, that's n. Yeah. But the harder part, I mean the counting technique, I talked about that, right? Yeah. So I do not repeat. So now the number of multiplications. Okay. It's a little harder than number of additions. Oh yeah, cut off. So next time I need to move, ½ inch about. Yeah. Too small. Yeah. All right. Now let me do a chart here. For each term, let's count the number of multiplications. This means multiplication, okay? Not x. Okay? Number of multiplications. Each term. Okay? The first term, A1x, 1. Okay? Second term, 2, right? Yeah, because square, you need to take the x times x. So 2 multiplications, and so on. Okay? Yeah. 3. Yeah. All right. Good. You know that formula well. Okay? The total, he gives that formula. I hope everybody knows that formula. Yeah, that's great. Yeah, I like to see that. I really. But for this class, we have a lot. We need to use a large number of formulas. Okay. So at some time, I want to collect. So actually, in our textbook, Appendix A, the author gives many formulas listed there. Okay? But I feel we may need to use more than that. Okay? We may double, triple that number. Okay? Yeah, because we need to use a lot of formulas. Double, triple that number. So I tried to list all the formulas we used in this class. So I prepare a document. Okay? So, PDF file and a document. So when you take the test, you can print out, you can take that document with you, all the formulas. Okay. All right. Yeah, the answer, yeah, so that's the formula. Okay? Yeah. So that's the formula. Okay? So we use directly. We do not need to derive it. Okay. All right. So we get that number. Okay? Yeah. That's the number of total multiplications. Okay. Now we can calculate total units of time. Yeah. 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 Right. Yeah. 10 times this number. Yeah. Because 10 units, right? Remember, each multiplication uses 10 units. 10 times 1/2, you get 5. That number. Okay? So after some simplification, we get an expression. Okay? 5n squared plus 6n. That number, precise, very precise number. Okay? So here you can see, if we have this expression, we do not need to know what computer do you use, right? So the supercomputer, it doesn't matter. We don't need to consider program, right? The quality of the program. Okay? If someone writes really slow, doesn't matter. Doesn't matter because this number is an absolute number. Everybody uses this number. So we can do fair comparison, right? Fair comparison. No other factors. Okay? All right. So that's the first step. Any question so far?